properties of self-adjoint or Hermitian matrices. Although I will be speaking about Hermitian matrices and self-adjoint matrices, what I'm about to discuss is somewhat true in operator sense. So if you have a Hermitian operator, what I'm trying to explain holds, but you have to change the meaning a little bit. Okay, so the first property is Hermitian matrices have real eigenvalues. Before we go on, I want to recap what Hermitian matrices are. These are something that if you have an inner product of two vectors, then applying A on one side is same as applying A on the other side. If this is true, we say A is Hermitian. Well, what is this inner product? Well, usually we're talking about this transpose V bar, but it doesn't have to be that. Actually, inner product is anything that satisfies the conjugate symmetry. So if you exchange U and V, this is true, and also it has to be linear in the first one. So if you had AUB BWV, that's same as AUV plus BWV, and also positive definiteness that UU should be bigger than 0 unless except when U is 0. In that case, you're going to get 0. Okay. So there are many examples that satisfy this property other than this one. One example would be, say, if you had like A, B, C column vector, another D, E, F column vector, and if you do a dot product, think about something that does AD but twice of BE plus 3 times CF. It's a little strange, but this nonetheless satisfies all the properties listed here. By the way, it should have a bar here. Okay, so this actually being a Hermitian matrix depends on what the inner product means. Another thing is in general, in function spaces, when it's infinite dimensional, if you have two functions f and g, and if they belong to some function space, some vector space made up of functions, then you can integrate them over some measure. So if this is a three-dimensional or some n-dimensional thing, you can integrate, and if you take bar on one of them, that also satisfies all the conditions listed here, except that this being positive has to be interpreted in some measure theoretical sense. So that's a little technical, but you can also think about inner products in here. In this context, you'll be talking about Hermitian operators rather than matrices. All right, let's move. Suppose U is an eigenvector of A. This means that A times U is same as multiplying some constant times U. Okay. This is the definition of C is an eigenvalue and U is an eigenvector. Okay. If this is true, then we want to show that C is a real number. Now, how do we do that? Well, think about AU, U. This is same as C times U because of our assumption here. And because it's linear in the first one, C can come out. And notice that since eigenvectors are never allowed to be zero vectors, this is really C times something non-negative, something positive. Now, recall that being Hermitian means A can go over to the other side, so it's U times AU. But then the conjugate symmetry says you can interchange this with a cost of bar. But what is this? This we know it to be C times UU, because it's exactly the same thing as what we have over there. And this part here, again, by the positivity condition, this is just some positive real number. So that's really same as C bar UU. Now, see that we have the same thing. We started with the same thing, ended up with these two different things. And the only way that these two things will be exactly the same is if C is same as C bar. And that's only true if C is a real number. Second, two eigenvectors of Hermitian matrix with different eigenvalues are orthogonal. So let's think about that one. AU, let's just say this is C times U. And let's say there's another vector, another eigenvector, where AV is, say, I'll use B, okay, BV. And C and B are different numbers. Now, in that case, think about the following. If I have AU, V, I calculate it one way because we know that AU is same as CU. And then C can be brought outside. We have this. And then use the property that A is Hermitian, so we move this to the other side, and you get, well, AUV is same as UAV, using the property that it's Hermitian. And then you use the fact that AV is BV. And then you can switch this around and move the B out, and the result is that this B can come outside, but it will have a bar on the top. Okay, and then for these two to be equal, you would want that C minus B bar to be B bar times UV equal to 0. So either one or the other is true. Either C is equal to B bar or UV equal to 0. But remember, we just proved that C and B are real numbers. Eigenvalues are real numbers if you have a Hermitian matrix. So saying that C and B bar are the same is exactly saying that C and B are the same. This is exactly same as saying C and B are the same, but that contradicts our assumption, so this cannot be. Therefore, the only way this is possible is if you have U inner product with V equal to 0, but that's exactly what it means to be orthogonal. Okay? If the dot product of two vectors is 0, then you say that the two vectors are orthogonal. Part 3. Hermitian matrices are completely diagonalizable, and a set of normalized eigenvectors of a Hermitian matrix form an orthonormal basis. Now, the full proof, the rigorous proof of this is rather involved, and I don't think I'll be able to show it to you. So I'll give you rather a heuristic argument. Now, first, you have to know that if C is an eigenvalue of matrix A, that means determinant of A minus C times I is equal to 0. And in fact, this is how, if you had a course in linear algebra, this is how you find all the eigenvalues of a given matrix, right? Now, there are many cases where A minus Ci, well, if you write this out, then it turns out to be a polynomial of C. And if A is an n by n matrix, then this thing will be an degree n polynomial. So this will have at most n distinct roots. If it doesn't have n distinct roots, then you may not have enough eigenvectors to diagonalize this. But in the case when this does give you n distinct roots, then what it means is that suppose. So I'll just try to prove in the case with the assumption that the important assumption is that suppose A has n distinct eigenvectors or eigenvalues. Okay, eigenvalues. In other words, you have this polynomial equation, determinant of a minus ci equal to 0, that becomes an order n polynomial, so it has n distinct eigenvalues. In that case, since all eigenvalues will give you at least one eigenvector, and there could be at most n eigenvectors, we see that there are n distinct eigenvectors. And because what we proved a moment ago, we know that these are orthogonal. If we name these eigenvectors as v1, v2, v3, and so on until vn, here's what happens. Think about this. If A times, write all these v1, v2, v3 until vn as column vectors, and if you multiply A, this is what happens. This is the same as C1, V1. C1 is the eigenvalue for eigenvector V1, C2, V2, all the way up till Cn, Vn. And this is actually same as V1, V2, Vn times C1, C2. It's a diagonal matrix that looks like this. You can check that this is actually true by doing the actual multiplication. Just do some examples with 2 by 2 or 3 by 3. You're going to see that this is indeed true. Now, what does that mean? If I move, well, let's call this matrix as P. Then this is what I have. AP is equal to P times some diagonal matrix, D, made up of entirely the eigenvalues of A. So if I move this to the other side, then I get P inverse of A, P, equals to D. So this shows that A is completely diagonalizable. Not only that, since V1 through Vn are orthogonal to each other, if we take V1 and divide it by its size, we take V2 divided by its size, and do that for all of these. We call this normalization, right? If we normalize everything, then all these vectors will be unit vectors, and since they're orthogonal to each other, this will be an orthonormal set with n vectors. So since our dimension of the vector space is n, that means this will be the basis for the space. Okay. So here's an interesting idea. So probably the most important thing that we're talking about here is the fact that if you try to take a Hermitian matrix, then if you find all its eigenvectors and normalize, then they form a basis for the underlying vector space V. In finite dimensional space, this is not that amazing, but if you have infinite dimensional vector space, so think about this example where you have a function which is differentiable twice. So f double prime exists on 0 to 1, and it's continuous, and also f of 0 is 0 and f of 1 is 0. Now if you think about the collection of such functions and you name it as omega, you'll see that any two functions that belong here, if you add them, it will again belong here, and you can multiply f by any other number, then it will still belong here. So you can easily see that this is an infinite dimensional vector space. And the Laplacian, which in this case it's just a one variable function, so you can only differentiate by x. So if you differentiate twice by x, remember the general Laplacian is plus a second derivative of y, and then if it's three-dimensional, second derivative of z, and so on and so on. So this, we know that it's a Hermitian operator, and in this specific example, you can just integrate, you can integrate by parts twice and show that this is indeed self-adjoint. Now, if it's self-adjoint, or you can even show that it's Hermitian, if it's Hermitian, then to use this idea that eigenvectors form the basis of V, you can think of it like this. You have this Laplacian times f, and f is a function, it's a vector in this space, and it's an eigenvector, so it's some constant times f. With these conditions forced upon it, it should be 0 on both ends. And if with some math, you can show that this actually ends up being f of x has to be some multiple of the sine function, sine n pi x. And your c has to be n squared pi squared. So what does that tell us? It actually tells us that this space has this as a basis. I didn't normalize this, but if you normalize it, you can even easily write down any other vector in here as a linear combination of these objects, and that's exactly what we call Fourier sine series. So that's where the importance comes in. Now, the general problem of having some boundary conditions and having a Hermitian operator on some function space, that's called Sturm-Liouville problem. Okay, so Sturm-Liouville gives you some Hermitian operator, and you have some boundary conditions so that this Hermitian operator is really Hermitian. And then from there we can have all these orthonormal basis function for the given space. So it's pretty cool.